Welcome back, y'all. In this video, I'm going to show a classic reaction in organic chemistry, the Skraup quinoline synthesis. It was discovered in 1880 by the chemist Zdenko Hans Skraup. I don't know much about 19th century history and the politics surrounding it, so I don't know if it's right to call him Czech. He was born in Prague in 1850, which is part of the Czech Republic today, but at the time, it was a part of the Austrian Empire. When he died in 1910, the Austrian Empire didn't exist, and he was in Austria-Hungary. There's a lot of overlap of countries in former empires in general, so it probably is correct to refer to him as Czech, but I thought I would clarify. So the Skraup reaction is a type of ring-forming reaction where aniline, glycerol, sulfuric acid, and nitrobenzene are mixed and heated. The aniline and glycerol form the structure of the molecule, and the nitrobenzene oxidizes one of the intermediates to form quinoline. I used a 1922 Orgson organic synthesis procedure, which modifies the original by adding ferrous sulfate to the mix. This lengthens the time of the reaction, presumably because the iron species serves as an oxygen carrier, and this is good because it's a notoriously violent reaction. It's so violent that under the original reaction conditions with no ferrous sulfate, it's more or less expected to undergo such an intense runaway reaction that the flask's contents blow out through the condenser. Thankfully, that didn't happen with my runs of the reaction, so the ferrous sulfate must act in the way that the literature describes. Some things did go wrong, however, which you'll see soon enough. To foreshadow events to come, think of Tom and what he often encounters in organic reactions that he runs. On to the video. Here are the masses of the reactants. The order is important because the sulfuric acid is what triggers the reaction, so to speak. I suppose everything other than sulfuric acid could be added in any order, but I try to stick to the procedures described in literature as much as I can. The ferrous sulfate I'm using isn't quite 100% pure, as can be seen by the color. It was made by dissolving a cast iron pan in sulfuric acid, but it was sufficiently pure for this reaction. I decided to do some maths and use the calculated amounts of aniline sulfate and sulfuric acid relative to the amounts of aniline and sulfuric acid used in the literature. Aniline sulfate is my source of aniline, and due to the losses in freebasing and purifying it, along with my laziness, I chose to use straight aniline sulfate instead, because that's what it's going to end up being anyway. I bought it from a seller on eBay. I'll put the link to his shop in the description. So in the literature, dynamite glycerol is used, which contains less than 0.5% water. USP glycerol, at least in 1922, contains 5% water, which is said to lower the yield. Thankfully, the chemical industry has undergone considerable advances in the last century, so even the everyday consumer, such as myself, can easily obtain glycerol of 99.7% purity. I made the nitrobenzene myself using a mixed acid nitration of benzene, of which there are several videos on the subject. I got a little over a 70% yield, and around 20 to 25% of my yield resulted in dinitrobenzene being formed, which was produced a bit more than expected because I let the temperature rise just a touch too much. So once I add all the reactants in the proper order, I heated the mixture for almost 15 minutes with my heat gun at the highest setting. Electric heat guns didn't exist in 1922, as far as I know, so the procedure says to heat the flask with a Bunsen burner flame. The heat gun was applied until the reaction took off, so to speak, until the contents of the flask were boiling fairly vigorously. Once I got to this point, I removed the heat gun and waited. The heat of the reaction was reported to be sufficient enough to cause refluxing of the flask's contents for 30 minutes to 1 hour, but this wasn't the case for me. It died down after only 15 minutes. I chose to wait for a full half hour just in case before I set the heating mantle up. Once I set the heating mantle up, I turned it on and refluxed the reaction mixture for 5 hours. Once the 5 hours was up, I shut everything down for the night. The next morning, I set up for steam distillation. Here's the full setup, kind of. There's one part that's missing, but I'll show it in a second. Yes, I have a lot of faith in the Keck clip connecting the gram condenser to the receiver adapter. So this guy right here is a commercial steam generator. It's marketed for use with a steam box for wood bending and cost me like $70. Has a capacity of 1.3 gallons, which is, I don't know, 5 liters-ish. I bought it specifically for steam distillations, and this synthesis involved a lot of it, so I tried using it. It's essentially a plastic tank with a heating element inside and tubing leading to whatever you want to slap with steam. I put an adapter on the outlet of the tubing and attached a short length of this fluoroelastomer tubing rated to a little over 200 degrees Celsius to the adapter and stuck a long glass tube of appropriate diameter into that. I used a one-hole rubber stopper to seal the glass tube into the distillation apparatus, and I think it's a number 4 to fit the 2440 joints of the flasks. In the procedure, it says when the reaction mixture is at about 100 degrees after the reaction time is up, transfer it to a larger flask from 5 liters to 12 liters, because this is a 5th scale version of the Orgson procedure. And on this scale, it'd be 1 liter to technically 2.4 liter flasks, but those don't exist. So just a 1 liter to a 2 liter. But I don't have a 2 liter flask or heating mantle, so I kept it in the 1 liter flask. I added about 150 milliliters of water to the reaction mixture, as when it would have been transferred, the flask would be rinsed with water, and it helps keep the temperature limited. Otherwise, it would get a lot hotter than I want it to, and that would mess with the steam distillation and the product, I'm sure. Because as you can see, there's a shitload of tar. Just great. I love it. In retrospect, it would have been smarter to transfer the mixture to another 1 liter flask, because there's enough tar in the original flask that proves to my shit up later. So I heat the mixture to boiling, remove the heating mantle, and insert the steam line. What's going to co-distill is any unreacted nitrobenzene, which is very steam volatile, while the acidic solution will retain the quinoline as quinoline sulfate and any unreacted aniline as aniline sulfate. Because the flow rate of steam is so high, a normal Liebig condenser alone won't cool the vapor fast enough, and too much will blow straight through the apparatus. I use a second condenser, a Graham condenser, in tandem with the first one in a downward distillation setup. Graham condensers are pretty much useless for anything other than downward distillations because the coil clogs if you try to reflux anything with it. It's perfect for this because any vapor that travels through the system has to pass through the entire coil, which ensures intimate cooling, and so long as the water in the circulator, which is a bucket, is cool, nothing escapes. So I ran the steam distillation until about 300 milliliters of distillate passed over. After this, I mixed up a 40% sodium hydroxide solution, that's weight for weight, with mostly ice and a little water to control the exotherm of the dissolution. After it's more or less dissolved, I began to add it to my still warm, tarry mess of a reaction mixture, and the neutralization of the sulfuric acid evolved so much heat that I had to cool it down in a room temperature water bath for a while before I resumed the addition. After it's all added, I rinse out the beaker with a little distilled water, then set up for another steam distillation. This time, I have to collect between 1.2 and 1.6 liters of distillate, so I have a 2 liter glass bottle on the receiving end. I shoved a folded length of paper towel between the bottle's mouth and the joint of the Graham condenser because I want to eliminate the possibility of creating a sealed system and blowing shit up. With everything ready, I turned on the heating mantle and shoved the steam generator tube into the apparatus. After collecting somewhere between 700 and 800 milliliters of distillate, disaster struck. Too much water was condensing in the still pot, it bumped a bunch, it overflowed, and some blew all the way through the system. I do think the tar is so black and opaque, and since it evenly coated a bunch of the glassware, it looks a bit like a pretty black mirror. This is bad though, so how do I fix it? Wait for everything to cool, transfer the contents of the flask to another vessel, and hopefully this tar stays into it, which it does, and then clean out all the crap. After 3 hours of chromic acid abuse, everything looks almost brand new, so it's time to commence the steam distillation, excluding the steam inlet from now on. It starts bumping when I get to boiling down the tarry garbage, but it pretty much goes smoothly and I call it good once I've collected 800 milliliters of distillate. I thought I'd have to redo everything up to the 1.2 to 1.6 liters of distillate again, but once I got to 800 milliliters, the distillate that was coming over was clear, thankfully. I want to end up with a final aqueous volume of 600 milliliters like the procedure does, so I separated the quinoline from the water using a separatory funnel and steam distilled the steam distillate. I steam distilled it directly onto the previously separated quinoline, and once I got 600 milliliters of distillate, I shut everything down, moved it to a stir plate, dumped in 30 milliliters of concentrated sulfuric acid, and the solution immediately clears up after converting the quinoline and aniline to their water-soluble sulfate salts. Then I put the flask in a bucket of water with cooling packs. While waiting for it to cool to 0 to 5 degrees Celsius, I dissolve 14 grams of sodium nitrite in about 25 milliliters of water. Once it's sufficiently cooled, I spill some of the sodium nitrite solution while swirling it, not enough to matter, and then dump it straight into the quinoline-aniline acid solution. There's an excess of sodium nitrite relative to what will react with any aniline present, so what's left over reacts with free sulfuric acid to briefly form blue nitrous acid, and the color quickly dissipates. I set it back into an ice bath and stir it for a little longer. Then I transfer the contents of the flask to a 1 liter round bottom flask and reflux it for an hour. The purpose of this step is to convert any unreacted aniline that steam distills with the quinoline to its diazonium salt, which is why it's acidified and sodium nitrite is added. Quinoline can't undergo this reaction because it doesn't contain a primary amine, while aniline does. Diazonium salts are unstable, and if you boil one in an aqueous acidic solution, it's converted into the respective phenol, which, for aniline, is phenol. Once I'm done refluxing, I'm about to set up yet another steam distillation. Before this, I'm going to show that there is nitrous acid present because if too little sodium nitrite was used, some aniline would be left over, which of course we don't want. If an excess of sodium nitrite really was used, there's going to be some free nitrous acid in the solution. The test uses a starch iodide solution made by adding 50 milligrams of starch, and I just use potato starch, made into a slurry with a little water, into 100 milliliters of boiling water. After it's added, a small chunk of potassium iodide is added to the almost clear solution and allowed to cool. I didn't want to wait, so I poured some into a test tube and dunked it in water to speed up the cooling. Nitrous acid is an oxidizing agent, and it'll oxidize the iodide in solution to free iodine, which will react with iodide ions to form triiodide ions, which will complex with the amylose present in starch. The triiodide amylose complex is blue-black in color, and the formation of this color is a positive test for nitrous acid. The test is positive, so I can confidently move on to the steam distillation. I have to do it in 2 batches though, because I'm not feeding steam through an inlet tube, so I distilled 500 milliliters, stopped, added water, and distilled 300 more milliliters for a total of 800 milliliters of distillate. Any phenol formed in the earlier refluxing step passes over as it's steam volatile. It's water-soluble, so the distillate is a clear, very dilute aqueous solution of phenol. After that's all done, I mix up another 40% sodium hydroxide solution to freebase the quinoline from the acid solution left in the still pot. Once I add it, you can immediately see the quinoline separate out. An important note is that quinoline is denser than pure water, but because the aqueous solution has salts dissolved in it, it's denser, so the liberated quinoline floats. I dilute it with more water so I can squeeze out more steam distillate and be confident that it'll be a continuous process rather than a batch-wise one. I could have done another steam distillation like I've been doing up until this point, but I want to minimize the amount of water collected for reasons that'll become apparent later. So I use a Dean-Stark apparatus. Quinoline is fairly soluble in water, even more so as the temperature increases, so while there is a layer of quinoline that forms at the bottom of the trap, there's going to be an appreciable amount in the upper aqueous layer as well, which can be seen by the cloudiness. I'm going to collect everything that's in the trap until there's no lower layer and the water is clear. This requires collecting about 250 milliliters of distillate. I transfer it to a separatory funnel, isolate the quinoline, and do another Dean-Stark steam distillation on the aqueous layer. I could have just used it as is, but again, I wanted to minimize the amount of water collected. Once I'm done, I add everything to a graduated cylinder to get a rough idea of how much sulfuric acid I'll need to neutralize the quinoline. Looks like about 52 milliliters plus whatever's dissolved in the water, and I'm sure there's some water dissolved in the quinoline, so this is probably overkill, but I use a little more than twice as much as the theoretical amount needed to make the bisulfate, which ends up being about 50 milliliters of concentrated sulfuric acid. After that, I boil it down to a reasonably small volume, add denatured alcohol, and repeat until I've minimized the water. Quinoline bisulfate is very soluble in water and less soluble in alcohol. It is fairly soluble in boiling alcohol, much less so in cold alcohol, so the quinoline bisulfate could be recrystallized from absolute alcohol if the melting point is off. Once I had a syrupy 100 milliliter solution, I cooled it down, and during this I spilled 20 milliliters of it, so I lost 20% of my yield, and I'll factor that into my calculations later. After pouring the 80 milliliters into like 250 milliliters of alcohol, then transferring it to a bigger beaker and adding more alcohol, I covered it and left it in the freezer overnight. My wash bottle of denatured alcohol was also chilled in the freezer. The precipitate is a light tan, kind of sandy color, and after the filtration is done, I try to squeeze it dry on the funnel with a rubber dental dam and rubber band. This works well, but I'm going to have to chuck it in the desiccator over sulfuric acid to get it fully dry. The reasoning behind isolating it as the bisulfate salt rather than its freebase form is purity and storage. Stored properly, the salt is much more stable against oxidation, whereas the freebase oxidizes and darkens even when stored in an amber glass bottle, along with being hygroscopic, which is annoying. So, after all that, I end up with 52.82 grams of, after being in the desiccator, a gray crystalline powder. It's very light gray, with a melting point of 161 to 164 degrees, close enough to the literature value of 163 to 165 degrees. It might not be completely dry, as some of it is chunky, rather than all of it being free-flowing. Maybe it is dry and the chunkiness is normal. It was in the desiccator under vacuum for 2 days, and I didn't want to wait any longer to try and get this video out. The yield was calculated based on the starting aniline sulfate. It's about a 66% yield. It's not great. Considering that multiple steps went poorly throughout the synthesis, I think this is an acceptable yield though. I think in the OrgSyn procedure, they got between 84 and 91% yield based on the aniline. Oh well. If I ever do this again, I'll figure out how to steam distill more better with my steam generator, not blow a bunch of crap through the entire apparatus by allowing it to overflow, and not spill any of my product in the 11th hour. That's about all I've got. Thank you for watching. If you want to, like, comment, and or subscribe, and I'll see you in the next video.